and also transcribed, you know. I find the transcription to be somewhat disconcerting, discombobulating, miscombobulating. No, the word is discombobulating. Transcribe that. All right, whatever. Perhaps I should speak more clearly and then it won't be an issue. Okay, so I erased that and I don't know, can I use a ruler? Does that work? Oh, look at that. Ah, it does kind of work, huh? And then that's a right angle. Oh, we don't know that that's a right angle. I take it back. All right, I'm gonna have to erase the whole thing. So we construct the midpoint here, right? And we don't know, wish I could see the ruler. Right. We don't know that that's a right angle. We only know what? That this is congruent to that, right? Because by definition, a midpoint. Now it's going to turn out that that is perpendicular, right? Okay, so we go down, construct a midline for, construct CD, a midline. Oh, this, wait. So let me label this point here D, right? Does that look like a D? Oh, now I've lost my, that's weird, huh? All right, so we have, there should be like an undo thing here, right? So let me try this again. So if I move this to here and say I'm drawing that, and then I get down here to point D. Does that look like a D? I don't know. So that's the point D. So MD is the, construct CD, a midline for triangle. So a midline is a line that connects the, okay, I'm gonna have to edit this, sorry, because it's not quite right the way it is. That, for instance, should be MD, right? AC is parallel, yeah. Okay, so that should be an MD. So I click on this little thing here and I get that. And I still got this little flat, never mind that. So this is good. So I have to say overline, and then I say it's MD, that's the midline, right? Okay, and then I'm gonna save this and scroll back there. Okay, so it's back to the way it should be, right? And now I've got construct MD, right? So I construct the midpoint, then I draw MD, which is gonna be a midline, meaning it's connecting the midpoint M of AB with the midpoint D of CB. And what do we know about a midline? Well, it's parallel to the, let's see if I can erase that. Oh, what happened there? Oh no, what did I just do? Oh, God, can I get rid of that? Okay, this is terrible. All right, so MD is the midline. We know that a midline is parallel to the base of the, sorry, a midline is parallel to the base of that triangle. Jeez. Oh, the base of that midline? I guess that's right, yeah. So what's the base of the midline? That's the side of the triangle that it's the midline for, right? So if the base is AC, then the midline relative to that base connects the midpoint of AB with the midpoint of CB, and that's this midline MD. Okay, so that's correct. So then I claim that MD is parallel to CB, it's perpendicular to CB now, right? And presumably I can draw in a decoration to indicate that. oh, I need to choose the pen object, and yeah, like that, right? So that indicates that it's perpendicular now. And how do we know? Well, a midline is parallel. So AC, we've established that AC is parallel to MD. And so you can either say altered interior angles or our corresponding angles are congruent. So the transversal CB is cutting parallels AC and MD, right? So it's making corresponding angles parallel and I mean congruent, so that the right angle at C is the same angle as the right angle at D. Okay, so then that's pretty much it, right? Well, let's see. Here we have then that angle ACM plus angle BCM. Oh, yeah, ACM and BCM are complementary, right? So when you those are, oh, I don't think I need that line, right? Sorry, I think that was left over from a previous attempt. I will edit that out. Okay, so I want to delete this row. Delete table? No. Delete row. Okay. Do I want this next row? No. Yeah. Okay. So now I'm going to save that. Sorry. A little bit of work to do here still. Right. So we're back to here. And let's see how things are going in the chat. Oh, Leonardo is here. Good. And Taylor Milligan is here. Did I get those people? Make sure. Probably this will now be in the transcript, right? Everything goes in the transcript. Taylor Milligan. Yeah, I had you here. And Leonardo, I did not, I believe. And that's Rodriguez here. Okay, sorry for the interruption. Okay, so we're back over here. And so now MD is a perpendicular bisector of CB, right? Well, it's perpendicular and it bisects, so that's just a definition. So MD is congruent to itself. That's the reflexive property of equality. So I have side angle side, and I can establish that triangle CMD is congruent to triangle BMD, right? And that means that corresponding parts are congruent, namely CM. Geez, there's another typo there. Do you see it? That should be a CM, not an MD. Yeah, which is what we wanted to show, right? Edit. God, didn't realize I was making so many mistakes. Okay, so I guess I have to get rid of that whole thing, huh? You can't just double click on it and edit, right? No. How about this? If I go here, yeah, okay, so there it is. And so I can just say CM here, does that work? Yeah, and then insert that. Okay, that's easier than retyping the whole thing, and then save that. Well, I'm glad I reviewed that because it did have some boo-boos in it, did it not? Okay, then I want to talk about principle. Any questions about principle 5 then? You know, it seemed fairly obvious, right? But again, the obvious is the enemy of the true, right? It's obvious that Oswald shot Kennedy. It's obvious. I saw it. Wait a minute. No, I didn't see it. Anyway, don't believe my lying eyes. How are we doing in the chat? Okay, everybody's here? Oh, no, that's going to be in the transcript too. And then it'll talk about the transcript. It'll have me talking about the transcript. All right. So principle 6. And I want to talk about principle 6. I didn't prove it here. Well, let me erase these things here. Yeah. I kind of like the slate thing with the writing. I mean, if I could write better, it would be much better. But at least, you know, it's like almost like writing on the board, right? Okay. Except somehow it's more slippery. Slipperier? Slipperier. Transcribe that. So the three medians of any triangle intersect at a point which is 2/3 of the way from the vertex to the midpoint of any median. Okay, so I'm going to try to prove this. I'm going to go to our other venue here, which is, and we're going to need a new idea for this, okay? The new idea, in fact, I think I state that here. It may be, and certainly it would be helpful to have the concept of similar triangles to prove this one. Certainly the proof that follows uses that concept, and I didn't finish that proof here, okay? So two triangles are similar if they are equiangular, right? It's not enough, so we don't have an angle theorem for triangle congruence, right? I wonder if I should move this down a little. Yeah, we don't have an angle theorem. Right? Why not? Well, because we need at least one side to be congruent for the triangles to be congruent. You can easily imagine like two equiangular triangles. I don't want to say equilateral. What I mean is like 60, 60, 60, right? A tiny one and a huge one. They're obviously not congruent. Congruent means I can put the little one on top of the big one and everything matches up perfectly. Not going to happen, right? Not if one is tiny and the other is huge. So, but we do have this, that if two triangles are equiangular, or another word for that is similar, then their corresponding parts are proportional. So let me write down what that means, okay? And for that, we want to go to our drawing board here. Okay, and I'm going to state that, right? If two triangles, and this is not actually in the review materials, but we'll need this. This is important in trigonometry. If two triangles are similar, and another word for similar here is equiangular, that is, they have the same three angles, then their corresponding parts are similar. So I guess I'll try to draw two similar triangles. So I'm going to have a little one here. Well, actually, one way to do this is to draw, draw a triangle. Well, let me try to do it with two separate triangles, all right, like this. So is there a way of copying this angle over to some other location, say over here? Yeah, probably. Let's just fake it. So I want to make this one like significantly smaller, okay? So clearly those are not congruent triangles, right? But they are equal. I'm claiming that they're equiangular, right? Or, I'm sort of saying that that's the way I built them, right? So that those angles, those are corresponding angles then, right? And if this is A, B, C, then it's customary to write little a, little b, and little c for the sides. And let's do the same thing here. D, E, F, and then we'll have little d, little e, and little f. So corresponding parts are proportional. So there's a lot of different equations we can write that describe that, right? So one would be sort of C, or let's say A is to D as B is to E. That ratio, those ratios are the same. That's a proportion, right? As C is to F. Right, so that'd be one, actually, or sort of run-on equation indicating those things are all equal, right? Those proportions are all the same. Those ratios are all the same, and so a proportion is an equation saying two ratios are equal. And another way of saying that is that, you know, A over C is equal to D over F. All right, so this is another equation we can say. Here's another one. A over B equals D over E. And, you know, we could also write, let's write it over here, okay? C over B, I guess. I don't know. There's a lot of different ways of writing ratio sides. So C over B is the same as F over E. Okay, we're going to get to circles today, believe me. But we're trying to want to do this. All right. Yeah, I don't know. Time is wasting. Any questions in the chat? No, it's just Leonardo saying he's here still. Okay, great. So, and maybe I should put another ampersand. This is like an and, right? When wondering what that's this is true, and all of that is true, and that's true, and that's true, right? That's what it means to be proportional, right? Oh, did I say similar? That's the wrong word there. Gotta use the right word. Proportional. You may have been wondering what I meant by that. I meant to write the word proportional, but I had similar on the mind, and so I wrote similar instead. Corresponding parts are proportional, right? And that's what all these equations are saying. Sorry about that. Okay, so so now we wanted, so the claim, so principle 6, I want to prove this. And we need this idea of proportion. Well, I don't know if we need it. I think we do. We need this idea of proportionality. The intersection of two triangle medians occurs 2/3 of the way from a vertex to the opposite side. I think I just, you know, said that from my own understanding of the theorem. Should we go back and read what it says here? The three medians of any triangle intersect at a point which is 2/3 of the way from the vertex to the midpoint of any median. To the opposite side is what I meant to say here to finish that statement. Okay, so let's draw a triangle and try to make it kind of scalene, like these triangles up there are kind of scalene, right? So maybe something like that. And I'll draw it over here on the right. That's not a right angle, right? So I'm trying to draw a sort of generic triangle, right? And how do I find the midpoints of the sides? Well, I could use a compass, right? I showed you this little technique where you, we're going to need to draw an arc like that. Draw it lightly, maybe. Can you see that arc? It's up here. Not the greatest contrast, right? So that's with the point at one vertex. If I draw the arcs for the point at the other vertex, I get that intersection point. You see those intersection points? So I line up, I drop my pencil. or Sharpie or whatever it's called. So if I line up these points of intersects of those arcs, right, then that's a perpendicular bisector. But I really just want this point. So that's a median point there. And I'm just going to measure this one because it takes too long to do all that. So that's about 1.5 inches, I'm going to say. A little bit less, but the way I've set this up, that's going to be the midpoint right about there. And the reason I don't just draw it freely, because it tends to be kind of an optical illusion. Like this point looks like it's closer to that vertex than to this vertex, but I think that's an optical illusion. Should we measure that as well, just to be sure, or to be more sure? So this is like almost 3.5 centimeters from there to there, and 1, 2, 3. Yeah, a little bit more. So maybe it is in fact closer to that one, but let's pretend that that's a midpoint. All right, and then we have this median line here and this median line here. And it turns out all 3 median lines are coincident, right? And so if I draw this, I'm not going to draw the 3rd one, but if I were to draw the midpoint here, it would be on this median line, would also go through that same point. And that point is in fact called the centroid. It's not the orthocenter. Remember what that is? That's if you draw the perpendicular bisectors of all 3 sides, that those 3 lines intersect at the orthocenter. This is called the centroid. It's a different center. And the property of the centroid is if I were to cut out this triangle, so all the mass is just, there's no other mass associated with the paper, just the triangle, it would balance on that point, right? I could put that on the tip of a compass point or something, and it would, the forces of gravity that pull to the right and pull to the left and pull up and pull back, those would all balance out. Okay, so I'm going to draw, so let's label some points. A, B, C, and I'm going to draw this triangle here. Yeah. Okay, and that's a midline. So DE is a midline. So what are we given? Triangle ABC with medians AE and CD. Then can I call it a midline? Let me try to make this fairly brief. You know, sometimes when you do those 2-column proofs, they get to be long-winded and perhaps overly detailed. You know, you want to be careful when you make a proof that you don't assume things to be true, which you haven't justified. But yeah, so we have the midline DE is parallel to AC, right? And how do we know that? Well, we proved it, right? So we just remember that we proved that. Okay. So what does that mean? And also, DE is half of AC, right? We also proved that, right? That the midline is half the length of the base. Okay, now I'm going to prove that, and so should we put an F here? So my sub goal here is to prove that triangle DEF, can you see that triangle? Yeah, I've got multiple views of this, and I think, you know, yours should be large enough to see that's an F. And so triangle DEF, do you see that that's similar or equiangular to triangle, right, I said DEF, so it'd be CAF, right? Why? Well, since, you know, since transversals and what are the transversals? Well, CD and AE, right? Those are transversals cutting parallels. Shall I indicate that these are parallel with a little arrow like that? I think that's good, huh? Make alternate interior angles. EDC, yeah, for CD, that's going to mean angle EDC congruent to ACD. And what else? Well, and let's indicate that on the diagram here, like so. Also, DEA, when the transversal AE cuts, right? Then we get DEA. Oh, the Drug Enforcement Administration is involved here. Jeez, that's scary. Congruent to DEA, that's going to be EAC. So you got two, all you need for two triangles to be similar is if two angles are the same, because if two angles are the same, so is the third. The sum of the interior angles is 180 degrees, right? So there's only one thing the third angle could be. If you know two of them, you know the third. All right, so thus by angle, right? It's meaning that all we need to know are two angles. Triangle DEF, and here's the notation for similar, right? You just draw a little squiggly line like that. I've got a little bit of stuff I can erase here, maybe. Yeah, whatever. Similar to what? Well, DEF, so the corresponding angles are CAF, right? And we know that the proportions are then the same, right? So we know that the proportion of AC to DE is in the proportion of 2 to 1, right? Because DE is half of AC. Did I do that wrong? I did that wrong. I got it upside down, don't I? No, I don't. I have it right. AC is twice as long as DE, right? Okay. I don't know why I thought it was wrong. All right. And so that means what else is true? Well, all the other sides are in the same proportion, right? In particular, you see it happening here? EF is going to be twice, oh, I went the wrong way about. AF is going to be twice as long as EF. And CF is going to be twice as long as FD. And that's kind of what we want to show, right? So, all right, how can I make this more clear? So I guess what we'd say is DC is equal to DF plus FC, right? So the ratio of DF to DC this is what we want to show is 2/3, right? Well, we write DC as DF plus FC, and we know we can. Oh, maybe I should have written that the other way about, right? Because I want to split up the numerator over a common denominator, and I have now. You can't split up the denominator under a common numerator. That's just not done, right? So let's turn that about and we'll say df. I'm running out of paper here, so I'm hoping that this will do it. df plus fc over df is equal to df over df plus fc over df, which is equal to 1 plus 1/2, which is 3/2, which is the reciprocal of 2/3. I'm going to say QED here because we need to move on. Any questions about that? So we've kind of proven what we wanted to prove, right? Yeah, that's a nice one, I think. I'm kind of tempted to sort of take a picture of that and post it in. Turns out you can't just cut and paste pictures. You have to like save them and then upload them. I don't know what Jadzia did. Did you come in? She said she did it with her phone, but I looked up and found a discussion about, you know, just pasting into the rich text environment, which is what this thing. So let me, yeah, I think I can just capture this, right? Let me make me smaller, or just turn me off, huh? And then I can, maybe if I angle it a bit. Okay, I'm gonna capture this like so. And go to a paint. Do I have a paint window open anywhere? That's smart settings. I guess I could do it here. Paint is a little bit easier. Yeah, here's paint. I'm going to close that one and this one and open this one. And let me show you what I'm doing while I do it. Sorry, need to get up the display capture. All right, so this is paint, right? And I've got something here that I want to get rid of. How do I do that? Well, I don't know. Good question. I just delete. I don't know, it seems to be stuck, doesn't it? So I guess file new, how about that? Then I'm just going to say paste into there. Okay, and I'm going to say crop then, right? Because otherwise I get all this other stuff in addition to what I have. And then I say save as, and it's going to give me a dialog window for the, I'll just put it on the desktop. And what do we call it? Centroid, Centroid 2/3. Okay, wait, whatever, right? So that's now a PNG file. Can I then, if I edit this, find that and paste it in there, right? And well, presumably I got a little embed image thing, okay. And I'm going to go to Canvas. I'm going to say My Files. I'm going to say Upload File. I'm going to go to the desktop and grab that, which is here, open it, and say Update. And there it is, right? Okay. So I guess we got some extra words up here. But given triangle ABC with medians AE and CE, then midline DE is parallel to AC and DE is equal to, since transversal, blah, 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 blah. Looks pretty good. All right. I mean, it's not as clean as it might be, but it's not bad. So I'm going to save that. And so now that's there. And let's go back to our modules. Where, what do we have? I don't know what's been going on. Homework 5, maybe. We did homework 4 yesterday, but we still have to talk about 5 and 6. Oh, that's midpoints. Oh, okay, that's, yeah. Where's the reading for circles? Proofs about, I thought I had the circles. I'll link to it. The circles chapter, there it is, okay. And it's saying it's so, you should beware, there are people, bad people on the internet who will, okay. And how far did we get? Yeah, we went through 11 and 12. There's some work problems. I think we talked about those, or maybe not a lot, right? Yeah, we were on tangents, right? And okay, I think I had oh, not home, but modules. Yeah, so I had posted this in there. Proposition 18 from book 3 of Euclid. And let's see what he has to say about this tangent, because this is sort of an important one, right? That the radius to the point of tangency is perpendicular to the tangent line. And he does it by contradiction. So I don't think we've done a proof by contradiction. And so this is a sort of important logical advancement. If you want to prove something, you can assume the opposite is true and show that based on that assumption, you lead to a contradiction. Then by the law of the excluded middle, which says something is either true or it's not, which, you know, some people reject the law of the excluded middle. And then, all right, well, we're going to accept the law of the excluded middle and say, you know, either this statement is true or it's false. We assume, we assume that the opposite statement is true. So I think this sort of deserves a little bit of discussion, right? So the converse of P implies Q. That's the implication symbol. P implies Q is Q implies P. That's terrible writing. Sorry, I'm working on this. So I think we can say this, right? And so yeah, that's true. We've already covered that, right? But if not P is false, then sorry, then it's just because it's so slippery, I think. Then P is true, right? So we assume that I say that FC is perpendicular. So there's the claim, right? You see the claim? If not, right? So that's he's assuming not that this is not true, right? So he's assuming the opposite. So if DE were not perpendicular to FC, then we could draw FG from F perpendicular to DE, and that would be a different line, right? All right, let's see if we can follow the logic here. And these are little hyperlinks to, you know, should we go there and see what's there? This is from book 1, proposition 17. In any triangle, the sum of two angles is less than two right angles. All right. Wait, so can we go back? Oh, what happened? Can't go back? Okay, yeah, I guess we're there, right, okay. All right, that's true. And Again, proposition 19 from book 1. In any triangle, the side opposite the greater angle is greater. Okay, so these are things that presumably we've proved, right? Oh, here's the law of sines. That's coming up in the trigonometry chapter. Okay, so since angle FGC, do you see that there? FGC is a right angle. Angle FCG is acute. And the side opposite the greater angle is greater. Therefore, FC is greater than FG. So FC would have to be longer than FG if FG is the perpendicular. Right, because then angle FCG would have to be an acute angle, and so it's smaller. Wait, so FC would have to be longer than FG because, yeah, the angle C here opposite FG is smaller than angle G opposite FC. But FC equals FB, right? Because those are both radii. Therefore, FB is also greater than FG. Wait, the part cannot be greater than the whole, right? Which is impossible. Therefore, FG is not perpendicular to DE. And so we've arrived at a contradiction, which means that P must be true. That is, FC is perpendicular to DE. All right, nice little proof by contradiction. Okay, let's go back. Where were we before we got here? Oh, I think we were here, right? And let me erase that. Okay. So tangent principles, so we got 1. A line is tangent to a circle if it is perpendicular to the radius at its outer end. Okay. A line passes through the center of a circle if it is perpendicular to a tangent at its point of contact. Right, so if you have a tangent line and you draw the line perpendicular at the point of tangency, then that line will go through the center. That seems, obvious enough, right? The enemy of the true. Tangents to a circle from an outside point are congruent. Okay, so AQ is congruent to AP. How would you prove that? Well, you draw these two triangles, right? And, or would you? What would you do? So we want to prove that. Should we write this out maybe? See how far we get before we get stuck? All right. How are we doing? It's now 11:53. Maybe we don't have time for all this. I know. Okay, I'm going to go not there. Here. Okay. And so principle. So this is circle principle 5. By the way, it's principle AL. I saw some people misspelling it LE. So LE is like a synonym for main. The principal reason we have principles, right? So the main reason we have principles. Those are two different principles, right? So this principle is sort of a rule that is true, right? And why is it true? Well, it could be that it's assumed to be true, so it's an axiom. So there can be different reasons for a principle to be true. But yeah, this is the principle that's spelled AL. And I remember when I started teaching at COD back in 1943, we had the Chaparral, it's the school newspaper. And they did an article on me because I was like one of the first math teachers to teach at COD. And like maybe the 4th or something to be full-time. The headline was "New Math Teacher Teaches Principles," and they spelled it wrong in the headline, whatever. Okay, so this is an AL principle. Oh, I think I have that wrong. How did I get that wrong? It's the other one, isn't it? Eventually your mind just gets turned around. This is the EL one. So you were right. Shall we I know we don't have time for this. Okay, let's not then. Okay. Principle. Okay. I'm gonna get out another Sharpie here because this one is drying up. So sorry about that. Circle principle. I was spelling Miss Principal the wrong way the whole time. Yeah. So they had spelled it PAL, which is the main one. Oh, the way you remember that is that the principal of the school is the main guy at the school. Duh. All right. Anyway, what do we got? Circle principle 5, which says that the segment from us. Oh, sorry, this is 4. I'll get this right eventually. Which says tangents to a circle from an outside point are congruent. Is that going to be in the transcript? That's embarrassing. They should outlaw these things. Tangents to a circle from an outside point are congruent. Okay, so let's draw a circle, and for that purpose, I will use our handy dandy circle maker. And hope that is dark enough to be visible on the DocuCam. Oh yeah, looks great. Okay, so do I have an outside point? How about this point here? All right, so I'm going to draw, and they call this A, they call this O. So they connect the point outside the circle with the center of the circle. They draw the tangent over here. I'm going to attempt to draw a tangent, and that's going to be intersecting about there. And then another tangent here. Intersecting about there. And they call these points P and Q. So what are we given? Well, circle O with tangents AQ and AP. Is that clear enough? Okay. So the claim is that AQ equals AP. They're congruent. So let's draw these triangles. And I think it's going to be that easy, right? Once we draw these triangles, it's just going to pop out at us, right? Because we know that this is perpendicular and that's perpendicular. So OP is perpendicular to AP. And OQ is perpendicular to AQ. Why? Well, we just proved that, right? By Euclid. We can cite the Euclid. And this is a solid reference, right? 318, I believe, right? That was book 3, proposition 18, which we just looked at and proved, right? Or read the proof. And that was by contradiction, right? How are we doing? It's now almost 12 o'clock. So we know that AO is congruent to itself. Well, the radii are congruent, right? These are radii of same circle. And we know that AO is congruent to itself. which may seem obvious enough, but that's the reflexive property of equality. All right, and what else do we know? So should we indicate that with a couple of decoration there? So now we have hypotenuse leg, right? Because these are right triangles. So that means that triangle AOQ is congruent to triangle AOP by hypotenuse leg. And so AP is congruent to AQ, since corresponding parts of congruent triangles are congruent. Great. Let's not belabor the point. Oh, you lost connection, Maria? Okay, I don't think I marked you as present. Okay, let me do that while I'm thinking of it now. Good to have you here. And we want to go back to the text, which that's this, right? Okay. So what is principle 5? The segment from the center of a circle to an outside point bisects the angle between the tangents. Right. So we get that by the same proof, right? So I could go, we're not, yeah. So let me add here as a gimme. Also, we prove principle with an LE. Sorry about that, folks. I can't believe I did that wrong. Principle 5, I'm sorry, which is that what does it say? The segment from the center of a circle to an outside point bisects the angle between the tangents from the point to the circle. Okay. So in other words, and let me not belabor this because we're short on time. Those, right? So those angles are the same because those are congruent triangles, right? And so AO will bisect angle PAQ, right? So that's principle 5. Okay, let's get here and keep going. Yeah. Two circles in varying relative positions. Okay, so they could be overlapping, they could be tangent to one another. That's figure 620. The line of centers between two circles is the line joining their centers, right? So that's a definition. And circles O and O prime are externally tangent at P. AB is the common internal tangent to both circles. Is there external tangent? Yeah, right? AB is the common internal tangent. EF is an external tangent, and so is CD, right? Those are external tangents. Circles tangent internally, so it could be one circle is inside the other circle, and they have a common tangent. Overlapping circles, circles O and O prime in this figure, overlap. Their common chord is AB. Do you see that? And if the circles are unequal, their equal common external tangents CD and EF meet at P, and the line of centers OO prime is the perpendicular bisector of AB, and if extended, passes through the point of intersection P, which, you know, we could prove, but let's say that that just appeals to our sense of symmetry, since we're short on time. Or maybe we'll relegate that to more notes in the module. Overlapping circles, oh, yeah, right, I got that. So circles outside each other, right, so that's figure 624 here, right? So if you have two circles that don't touch at all, then they have, what do we call these things? Internal tangents, AB and CD, meet at P, if the circles are unequal, their common external tangents, they've extended, meet at a point P prime, right? So EF will also be congruent to GH, and if extended, those will meet at point P prime. The line of centers OO prime passes through P and through P prime, and also AB is equal to AC and EF is equal to GH. And then we get a bunch of solved problems. And I don't know, can you see how you would prove all these things? Yeah, let's discuss the proofs later. Let's try to at least just brush up against the concepts, right? So they have a bunch of solved problems, and then they talk about measurement of angles and arcs in a circle. We talked about this a little bit earlier, but a central angle has the same number of degrees of the arc it intercepts, right? So in this thing, so the central angle BOC here is 90 degrees, and so we say the degree measure of that arc is 90 degrees, right? And this was a sort of a difficult concept because I remember earlier when I asked for clear and fuzzy, people said they didn't quite get how you could have two arcs of different lengths with the same, well, two arcs, so if you have concentric circles, the one with a bigger radius is going to have the longer arc, but its degree measure is the same, right? Do not say that the central angle equals the intercepted arc. An angle cannot be equal to an arc, right? Because they're different things. But the degree measure of the central angle is equal to the degree measure of the arc, right? An inscribed angle. Oh, okay, here we're starting to get interesting, right? So if you have two chords, then the inscribed angle is BAC, right? So if you have two chords from a common point on the circumference A, so AB is a chord and AC is a chord, then they make angle BAC. And here are some principles. A central angle is measured by its intercepted arc, and inscribed, so this is an inscribed angle, is measured by 1/2 the central arc. And we'd like to prove that. Let's get started on the proof, and we'll finish it up at the beginning of the hour tomorrow. So I will set us up for proving this, if I can get over here to do that. Do I need a new sheet of paper? Probably, huh? So let's get a new circle. We'll make it a little bit bigger, maybe. 1/2 the central angle subtended by that arc, huh? Okay, this is a good one. Oh, are you? Yeah, you've seen that. So I've got the center of the circle O here. I've got a point on the circumference A, and I'm going to draw. It matters, but the theorem is true whether or not it's true that arc AB is on one side and of the center, and arc AC is on the other side of the center. So the claim is this, that the degree measure of inscribed angle, right? It's inscribed because it's not central, and A is on the circumference, right? Angle BAC is 1/2 the central angle BOC. So should we draw the central angle? And this will be very relevant when we get into trigonometry. So that's a quadrilateral in there, isn't it? Yeah, it's what's called a dart, right? It's not convex, it's concave, but it qualifies as a quadrilateral. Okay, and so this angle here is half this angle here. That's what we want to prove, right? The degree measure of that angle is half the degree measure. And we're out of time. It's 12:10. And I'm kind of going to try to be strict with myself about ending on time. Do I have more comments here? It's just Maria saying she got lost connection. Sorry about that. Good internet connection is hard to come by sometimes in some places. All right, any questions before we quit? So we're gonna start tomorrow with proving this claim, okay? And you might want to research it, you know, look up a proof of this claim. It's going to involve actually dissecting the. Oh, here I am starting to do it. I'm not going to do it. Okay. we're gonna draw AO and extend it out. I don't know. Do we need to extend? Yeah, we're going to extend it out, right, to point D on this opposite side. All right. So I'm going to wish you a pleasant afternoon and go to my office hours. Ciao for now. How do I? Oh, I have to. Okay. Bye, everybody.
Take care, Professor.
You too. Did I mark you there? Yes, I did. You bet.
Thank you.
All right. You too. Bye, everybody.